My name is Patrick, and today I'll be discussing Lab 3, which is circuits and capacitors. This is the outline of my lab. We'll start with the introduction and go over the additional questions. In this lab, we will analyze the consequences of series and parallel resistors, and then measure the potential differences in conventional current with multimeters, and then simulate the operation of capacitors and ohmic resistors. So some of our final results from this lab are shown in the picture below, where R wire and R ammeter are equal to 0 ohm. So the formulas that we will use in this lab depends on the Ohm's law, the loop rule, the node rule, the potential difference of a capacitor, the capacitance of a capacitor, and the lab-specific formula for calculating the RC. So the material used for this lab is the circuit construction kit, where we will construct the following circuit shown in the picture on the right, where we can find 2 batteries, 2 resistors, and 2 ammeters. So starting with the charge conservation and energy conservation in series circuits, from the Ohm's law, where V equals to IR, we find out that E1 equals to E2 equals to 0.02 amps. And now if one of the ammeters is replaced by a voltmeter, we will get the same I, and delta V equals to 3 volt. So when the circuit is closed, we will get also the same delta V, which is 3 volt, and delta V for 7 ohm equals to minus 0.961 volt, and the sum of delta V's will be 0. So this is a graph about the charge conservation and energy conservation in series circuits. So it's interesting to see the steps of the process, which actually confirms our results. So when we attach the voltmeter to alter the circuit, why doesn't the ammeter read change? Well, the voltmeter has very high resistance, meaning a very little current flows through. So the ammeter reading doesn't change. And if we replace the voltmeter with an ammeter in the parallel with the 100 ohm resistance, what happens to the current through the other ammeter? Well, both ammeters have a current intensity of 0.06 amps. So on the picture in the right, you can see the resistance of resistors, wires, and ammeters with the results which we talked about a few slides ago. Moving on to some principles before diving into some examples, we can see that the energy conservation shows that delta V capacitor plus delta V resistor equal to 0, as well as Q over C minus IR, and the differential equation I equals to minus dq over dt produces a function. Now for the capacitor charge as a function of time, we can see that as the capacitor discharges, the voltage and current decrease exponentially, and RC is time constant. Now if we plot ln delta V over delta V0 versus time, we will find a slope of minus 1 over RC. So now let's talk about some specific observations we did in our example. So what will happen to the light if the bulb is connected to batteries and capacitor in series? Well, the bulb becomes very bright, then dims until it is off. And what happens to the light when the bulb is connected to charged capacitors in series? The same thing, the bulb becomes very bright and dims until it is off. And what will happen to the current in the circuits in both scenarios? It starts off as a large number, then decreases until it reaches 0. And we find out that the time for the capacitor to discharge at 10 seconds at R equals to 10 is equal to 9.5 seconds, and R equals to 20 ohm equals to 18.2 seconds. So here is a quick table regrouping all the results and observations we did. I'll just give you some time to explore all the records I have done for this experiment. And now I'm going to talk about 2 important graphs for our lab. The first one, which is the time-dependent voltage across a discharging capacitor for RC circuits, which shows the potential difference delta V versus time. You can see that the slope is decreasing exponentially and reaching a value of 0 volt in the future. And now for the second graph, which is a linear graph that shows ln delta V over delta V0 versus time, we can apply the formula minus 1 over RC and find the RC of our example, where we got the value of 5.98. And now for the additional questions. So what if we were doing this lab in real life and use an actual ammeter instead of an ideal simulated ammeter? Well, the ideal ammeter has no resistance. A real ammeter has a small amount of resistance, which causes lower current values. And what if we used a real battery to charge a real capacitor with no resistor in the circuit? Yeah, well, the real capacitor will have a small delay before charging. Thank you.